All right, welcome to IE 325 Simulation, Modeling and Applications course. I'm going to be your lecturer this semester, and we are immediately starting with our first chapter, and I'm sharing my presentation file. Now, the first module of this course is going to give an introduction to the concept of simulation, and we are just going to follow the outline here. First, we are going to define what simulation is. Then we will mention in which cases or in which type of problems simulation can be an appropriate tool to use and when simulation is not appropriate to use. Now, in literature, many scientists discussed that there are advantages and also disadvantages of using simulation for problem solving, and there are certain areas of application. Actually, there are too many, and we are just going to mention about those. Then we are going to talk about the system concept. The system concept is an important concept to understand because in simulation, we are basically creating the models of systems. So first we need to understand what a system is and the components of a system. And we are going to classify systems into two classes such that systems that are discrete and systems that are continuous. Then we are going to talk about the model. So what is the model of a system? Because in simulation, we are basically creating the model of a system. We will define this concept. We are going to talk about the types of models and types of specifically simulation models. Finally, in the last phase of the introduction module, we are going to talk about the discrete event system simulation. Actually, in this class, what we are dealing with is discrete event system simulation. Though the name of the course is simulation modeling, in the undergraduate level, we mainly focus on discrete event system simulation. There are other types of simulations as well, but these are not a part of this course. So we are going to define the discrete event system simulation and the steps that we need to follow if we want to perform discrete event system simulation. Actually, creating a simulation model and running simulations to solve problems is a long-term project. Okay, so it is not just an immediate thing that you can create, you can perform and solve your problem immediately. It is not just like writing an algorithm and solving it in the programming environment immediately. It takes some time. Therefore, most of the simulation applications are actually long-term projects. So let's start with defining the concept of simulation. Here we have the definition. A simulation is the imitation of the operation of a real-world system over time. Okay, so it says imitation, and we have a real-world system. So usually we use the simulation technique to solve some problems related to some systems. And these systems are, of course, real-world systems. So if they were not real, why should we try to solve their problems, right? So we have a real-world system, and that real-world system actually operates. Okay, so it's a dynamic system, and it operates through the time. And in simulation, we are trying to create an imitation, a fake version of this operating real-world system. Now, here it says simulation involves the generation of an artificial history of the system. So it generates an artificial history. We need to understand this concept. What is an artificial history, or how can we generate an artificial history? And then the observation of the artificial history is required to draw inferences on operating characteristics of the system. So basically, we are creating a fake version, imitation of the original system, and this fake version creates an artificial history of the original system. So that artificial history is also fake, actually. However, we are using this artificial history to make inferences, draw inferences on the operating characteristics of the original system. So the definition here is, I think, comprehensible, but in order to understand it better, I think we need to understand what a system is and what artificial history is and how can it be generated. Okay. So how can we observe the behavior of a system as it evolves over time? Now, either you can observe it directly, but I mean, if this system is a slow-moving system, it is just going to take some time to understand the behavior of system. For example, if you are trying to understand how a warehouse is working, it is not just going to be sufficient for you to observe the system for half an hour. Okay, so if you really want to understand how a warehouse is working, maybe you need to spend at least 3 months in the system to observe everything so you can understand every aspect of the behavior of the system as it evolves over time. Now, we can also use another thing. We can use the simulation model. So we can create a model of the original system and we can observe the simulation model. And because the simulation model is going to be created in an artificial environment, such as in a software or a programming environment, you can increase the speed of the flow and you can watch it almost in a minute, maybe all 3 months of scenario can be watched in a single minute, and so you can observe the main aspects of the behavior in a faster manner. Okay, so instead of the original system, the model here helps to investigate a variety of what-if questions about the real-world system. So we may ask, for example, we have a warehouse, it has two doors where the imported materials are collected. Now, in order to expand the warehouse, we are going to open another door. Imagine. So, opening another door, constructing another door into the warehouse is costly. Okay, it is expensive and it takes some time to implement. So, what we are going to do is, before investing so much money into it, we want to see what happens if we open a new door, a new entrance for the imported materials into the warehouse. So this is a what if question. What if we had another door? Okay. Now, in order to answer that, you can either really construct a new door and see what happens after that, but this means you are going to pay the costs already. Okay. So there is no turning back from that decision. Or you can create a model of the original system, and over that model, you can perform experiments where you are opening a new door, maybe another new door. Okay, maybe you can increase the number of entrances to 4 or 5. I mean, you can try anything in the artificial environment. Okay, so the model here helps to investigate these what if questions. And these what if questions can be summarized as what would be the impact of the changes in the system to the performance. Okay. Now, there are models of systems which are very simple, and these models can be solved by mathematical methods. For example, the models that we use in probability theory. For example, a random variable is actually a model of a real life quantity. Okay. Or differential calculus. So a set of differential equations, linear differential equations, can model the behavior of the stocks in real life. And mathematical programming can help us to create optimization models of systems where we have an objective function and many restrictions on resources, right? So these models are simple. We can use simplex algorithm, we can use numerical integration, we can use numerical methods to solve differential equations, to solve all these mathematical models. But in real world, too many systems are complex. Okay, so we cannot simply use the models that we have learned in these courses. Sometimes, in order to solve real world problems, we need to create a complex model of a real world system. And in that case, the computer-based simulation approaches would be the only solution method for us.